Greetings, Panthers. Part 2 of our video about oxidation-reduction reactions, and I've pulled this equation forward from the last video and the oxidation numbers that we assigned. I have not told you why you have to assign oxidation numbers yet. That's what we're going to do at the end of this video. But first I want you to practice writing oxidation numbers down. So I've given several different examples here. The last one is the most difficult. I'll walk you through how to do that. But let's try to assign oxidation numbers to each element in these different species. And probably a good thing to do right now would be to stop the video and see if you can do it. And I will come back with the answers on how to do these. Okay, so let's take a look at this first one, SO3, sulfur trioxide. And remember, I'm going to set up this little table here. We know this is a neutral molecule. There's no charge on it. And if I look at these, I have sulfur and oxygen. And hopefully one thing you got out of the last video is don't try to memorize that periodic table. There's just way too many exceptions and variables. But you want to identify the ones that you do know something about. We don't know about sulfur, but we do know that oxygen is usually -2. So let's just put a -2 next to the oxygen, and there's 3 of those. So therefore, the total contribution from the oxygens is -6. I said this in the last video, I'll just reiterate. You are assigning an oxidation number to each element. So there are 3 oxygens, each one's getting a number assigned of -2. And in order for this to equal to -6, that tells me that my sulfur has to be contributing +6. Now the last thing I have to do is to say, how many sulfurs do I have? Well, I only have 1 sulfur, so therefore the oxidation number for sulfur has to be +6, and the oxidation number for oxygen has to be -2. Now if you're looking at this, you might be saying, well, wait a minute, these aren't ionic compounds, so why is sulfur a +6? That's actually the point. Oxidation numbers are not charges on ions. This is a molecular compound. SO3 is a molecular species, so these are not ionic species, but we can assign this sort of electron bookkeeping trick. So this does not mean there's a +6 charge in the sulfur, it just means we've assigned this trick called an oxidation number to this sulfur, and I will explain to you in a couple of minutes why we do this trick. All right, let's take a look at the next one, sodium phosphate. So we have Na3PO4. We note that that is a neutral species. So if I set up my little table here, that has to sum up to 0. We have 2 of them that we know something about. We know something about sodium, and we also know something about oxygen. The thing we know about sodium is that's a group 1 cation. Those are always +1. There's 3 of them. So the sodiums are going to contribute +3. The oxygen is usually -2. And in this case, it's also -2. It's not a peroxide. So this is going to give me a -8 contribution from all the oxygens. So that tells me that the phosphorus contribution of all the phosphoruses have to be +5, but since there's only 1 phosphorus, that tells me that phosphorus is indeed +5. So we got +1 for sodium, +3 for phosphorus, and -2 for oxygen. Again, I've said this a couple times, let's restate it. That -2 is each oxygen is -2, and there's 4 of them. That's why they're contributing -8. All right, I'm going to let you take a look at the other ones, and I will come back in a second with the answers, and then this last one we'll take a stab at. That one's a little bit harder. Okay, so if you did this the system I told you, you should have come up with gallium is an oxidation number +3, oxygen is -2 for gallium oxide. NO2 minus, you should have come up with nitrogen as +3 and oxygen -2. This one is a -1, so the sum of the oxidation numbers has to add up to -1. This one's a -2, this chromate ion, chromium +6, oxygen -2. And let's take a look at this last one, chromium sulfate. So one thing we notice is it is a sulfate anion. So you could just figure out the charges or the oxidation numbers on the sulfate anion. So I'm going to show you 2 ways we could do this. Sulfate is SO4 2-. And so one way we could do this is we could just isolate out the sulfate ion. And we know that this has to add up to -2. So We don't know what sulfur is. That one varies a lot. But we know that oxygen is usually -2. So this is going to contribute -8. And that tells me that the sulfur has to be +6 in order to result in a -2. There's only one sulfur. So +6 is one way we could do this. Obviously, oxygen is -2. The other way we could do this is we could take this molecule and we could say, well, that's got to be neutral overall. And we know that the charge on the chromium ion has to be +3. How do we know that? Well, that charge, it's a -2 here. 2- is the ion. This has to be a 3+ in order to cross this down and end up with these subscripts. Okay, so you have to have some knowledge of how you write ionic equations in this case. So that tells me that chromium is a +3, and there are 2 of those, so they're going to contribute +6 overall to this structure. We also know that oxygen is -2. 2 times 4 is 8 times 3, so this is going to be -24 is my overall contribution. Where's the -24 coming from? Well, I've got 3 times 4 oxygen, so I got 12 oxygens. Each one is -2. Therefore, they're contributing -24. So that tells me what's left over is +18 is what's needed up here. And so now I have sulfur. I've got 3 sulfurs, and so 18 divided by 3 is going to equal to +6. So either way, I could come up with the same answer. So when I'm writing down my final oxidation numbers, chromium is +3, sulfur +6, and oxygen -2. Remember, this is only being assigned to each individual chromium atom. So each individual chromium atom has an oxidation number +3, each sulfur has an oxidation number +6, and each oxygen has an oxidation number of -2. Okay, so hopefully you're able to take these compounds and convert them into oxidation numbers. And now I'm going to show you why we want to use these oxidation numbers. So recall we started this discussion with this equation. Redox reaction, I told you if you see one changing from, in its unbonded form to bonded, you know it's a redox reaction. So this is a redox reaction. And you also remember there's this little trick we can use, oil rig. And that stands for oxidation is losing electrons, and reduction is gaining electrons. So this is great. If you know which species is oxidized and you know which species is reduced, you can say which one's gaining electrons and which one's losing electrons. If you know it's oxidized, you can say, well, that one's losing electrons. If you know it's reduced, you can say that one's gaining electrons. Here's my problem with this little trick. When you look at an equation like this, or like these ones down here, you don't see electrons in this equation. Now look, they're there. One of them's losing electrons, one of them's gaining electrons, but it's not obvious from looking at this equation where the electrons are. Now in Gen Chem 2, we'll teach you how to write what are called half reactions, and then it's much more obvious where the electrons are going. But when you see a molecular equation like this, even a net ionic equation, it's not really obvious where the electrons are. So I'm going to show you a trick using the oxidation numbers to figure out which one's oxidized and which one's reduced. Once you identify which one's oxidized and which one's reduced, then you can say which one's losing electrons and which one's gaining electrons. So here's what I like to do. I like to take my accounting that I've done and sort of figure out what's happened on the reactant side of the equation and the product side of the equation. So what I do is I write down the oxidation numbers for each of the species on both sides of the equation. So zinc, I observe, goes from 0 to +2. Hydrogen goes from +1 down to 0. And chlorine goes from -1 to -1. Okay, so all I've done is I've taken the oxidation numbers, which we already found, and I write down on the reactant side what the number is and on the product side what the number is. And then here's my trick. And I don't think anyone else, I've never seen anyone else do this. If the number goes down, it's reduced. Oxidation number goes down, it's reduced. Oxidation number goes up, it's oxidized. Okay? I think this is a much simpler way to do it. You have to be able to assign oxidation numbers, But once you're successfully assigned oxidation numbers, you can just say if the number goes up, it's oxidized. If the number goes down, it's reduced. And down reduced makes sense to me. Number goes down, it's reduced. This one does not change at all. This one's actually a spectator ion. We could write a net ionic equation that would be simpler without including the chlorides, and that's actually borne out by the fact that the oxidation number doesn't change at all and is not involved with the reaction. Couple of points. If you see an oxidation number change from one side to the other, that is the telltale sign that you have a redox reaction. And if you know that one of them changes, something else has to be changed. So in other words, if you identify that something's reduced, then there has to be one that's oxidized. Okay? So these oxidation numbers are actually very powerful because they let you know, first of all, is this a redox reaction? And you can convince yourself with precipitation reactions and acid-base that the oxidation numbers don't change. If you identify that it does change, then you know that there has to be another species that also changes. And if you use my trick here, if it goes down, it's reduced. If it goes up, it's oxidized. Now, once you know it's reduced, okay, that one actually is gaining electrons, and oxidized actually losing electrons, which makes sense. It's going from a zinc 0 to a zinc 2+. It must be losing electrons in order to do that. One more little complication, just a historical problem. Species that are oxidized are also known as the reducing agents. Electrochemistry was discovered long before the knowledge of electrons, so these names came about before they understood what electrons were. And something is reduced is also called the oxidizing agent. So you may have a problem that says identify the oxidizing agent or identify the reducing agent, or which species is oxidized, which species is reduced. It's really not that hard, it's just the opposite. Whatever the agent is the opposite of the one that's oxidized. So let's take a look at a couple of problems, couple example problems. I want you to label the oxidizing agent and the reducing agent in the following reactions. So our strategy for this is to identify the oxidation numbers of each species. You can use my little trick here. If you want to use oil rig, that's fine. I don't see where you're going to see the electrons from, but okay, that's fine. And then we want to identify the oxidizing agent and the reducing agent. So this would be a good time to stop your video, see if you can identify the oxidizing and reducing agent, and we'll come back with some answers. So we have aluminum and fluorine in this first problem. Aluminum goes from an oxidation number of 0 to +3, and fluorine goes from an oxidation number of 0 to -1. So the one that goes down is reduced, and that would also be known as the oxidizing agent. And therefore this one must be oxidized and would of course be known as the reducing agent. Okay? Second equation, we have iron and sulfur. So iron is going to go from 0 to +2, and sulfur goes from 0 to -2. And again, this one was oxidized, this one's reduced, this one's the oxidizing agent, this one's the reducing agent. And the final equation, this one's not quite as easy. These are easy to see because they're all by themselves. These have compounds for each thing or almost each thing. So in this case, we have 3 different species. We have iron, we have oxygen, and we have carbon. So the iron goes from +3 to 0. So that tells us already this one's reduced. And that means there must be another one that's oxidized. This is the oxidizing agent. Oxygen goes from -2 to -2. It's not really a spectator ion, but it's also not really involved in this reaction directly. And then the carbon goes from +2 to +4. So the carbon is actually oxidized, or also known as the reducing agent. Now, just a little technical point to, if you have an exam and you have to identify, the oxidizing agent is actually Fe2O3, and the reducing agent is actually CO. Okay, so the reducing agent is actually this entire species, and the oxidizing agent, or the one that's reduced, is actually the iron oxide. Okay, so be a little bit careful with that. The iron is the one that's reduced, but the iron oxide is the reducing agent. The carbon monoxide is the reducing agent. Okay? So hopefully with this primer, you should be able to tackle most of the relatively straightforward, simple oxidation-reduction reactions. You should be able to identify which species is reduced, which one is oxidized, which one's the oxidizing reducing agent, and then of course, if you can do that, you can identify which one loses electrons and which one gains electrons. The key to doing this is being able to write down oxidation numbers for all the elements in the reaction. All right, thank you for watching. Talk to you soon. Bye.